Okay, so hopefully you guys all have a basic understanding of reflexive relationships, anti-reflexive, symmetric, and anti-symmetric. So just a real quick review. Reflexive means that for every single element in the domain that you're talking about, it's related to itself. Okay, that's what reflexive is. Anti-reflexive is there isn't a single element that's related to itself. Okay. Then symmetric is if x is related to y is related to x. Like they go back and forth. Okay, you can't have one without the other. Anti-symmetric is if you have one, then you don't have the other. Right? So if x is related to y, then y isn't related to x. And then there's this little caveat where you can have neither x being related to y nor y being related to x. That's like the tricky case with symmetric. Because if there's no relationship between x and y at all, then that could give you something that's both symmetric and anti-symmetric. Okay. Our last property is transitive. Okay. And so a relation on a set, A, that's the domain of the relation, it's transitive if we always have, for any three elements, when x is related to y and y is related to x, so notice that this is the same thing, this y and this y, these are the same thing, okay, then x will be related to z. I think of this y as the middleman, okay. So this y kind of creates a bridge between x and z. So x is related to y is also related to z, and that y is kind of a bridge between x and z. So x will also be related to z. Okay. So let's think about some of the relations that we know and whether they are transitive. Okay, so first of all, the less than relationship. Okay, so going to our definition. Okay, would it be true that if we had that x was less than y, that's our relation, okay, being less than, and we had that y was less than z, would that imply that x is less than z? Oops. Yeah. Yes. Yes, of course. Like that's the way that numbers work, right? If x is less than y is less than z, then there's this kind of ordering relationship among numbers where we know that x has to be less than z as well. So this is true, of course. Yes. So if the answer to that question is yes, then it's transitive. So this one is transitive. Okay. Let's think about the divides relationship. Okay, so let's say that we had x divides y and we had y divides z. Okay, would that imply that x divides z? This one's a little bit trickier. We can kind of go, all right, so we know that if x divides y, then that means y can be written as some integer times x. We know that if y divides z, that z can be written as some integer times y. Now, if we take this expression that we have for y and substitute it in over here, then we're going to get that z is equal to b times ax. Okay. And so, is it true that x divides z? Yeah, it is, right? Because here we just, this x divides z, if we can write z as some integer multiple of x, and we can. B and a are both integers, so z is definitely an integer multiple of x. So yes, this will always be true. Okay, so this one is transitive. Let's think about this last one. So let's say x is related to y if x is 2 times y. Okay, so let's say that we had x is 2 times y, and then y was related to z. So we have y is 2 times z. Okay, would it be true that x would be equal to 2 times z? So would x be related to z? Okay. All right, so once again, we can kind of do what we did up here. If we solve this one for y, we would get that x divided by 2 is y. And then if we substitute that in over here, we can get a relationship between y and z. So we would have x over 2 equals 2z, or that x would be equal to 4z. Okay. So if these two things are true, will that give us that x is equal to 2z? No, we would get x is equal to 4z. The answer here is no, that we will not get that x is equal to 2z. So this one is not transitive. And you could even just come up with one single counterexample, okay, if you don't want to make a general argument. Okay, the nice thing about proving that something is not transitive or not reflexive or not symmetric is you only need one counterexample, okay, to show that it's not true for all x, y, and z. Okay. But this general argument is fairly convincing that it's not true. All right. So those are all of our relations. Okay, our properties. We have reflexive and of course anti-reflexive, symmetric, anti-symmetric, and transitive. We don't have an anti-transitive. Okay. So let's review those with a couple different examples and make sure we really have a handle on these properties. Okay. So the term relatively prime refers to two positive integers. They're relatively prime if their only common factor is 1. Okay. So they don't have to be prime numbers. It's just that when you look at their factors, their only common factor is 1. That makes them relatively prime. So, for example, if we thought about 5 and 11, those are both prime numbers. Okay. And so if you think about 5, its only factors are 1 and 5. 11, its only factors are 1 and 11. Okay. And so 5 and 11 will be relatively prime if their only common factor is 1. Okay. Well, certainly 1 is their only common factor. Okay. So any two prime numbers are also relatively prime. Okay. But when we come to these numbers, these are composite numbers. They clearly have factors besides 1 in themselves, like the factors of 10 are 1, 2, 5, and 10. The factors of 25 are 1, 5, and 25. Okay. So even though these numbers aren't prime, they are relatively prime to one another. And they aren't relatively prime to one another either, because in addition to having this common factor of 1, they also have this common factor of 5. Okay. Okay, so these are not relatively prime. They have 5 as a common factor. Okay. And these are composite numbers. You might say, sure, I was going to guess that. They're composite. But here we have some more composite numbers. Okay, if we think about the factors of 26, they're 1, 2, 13, and 26. The factors of 33 are 1, 3, 11, and 33. And if you look at their factors, the only thing they have in common is 1. Okay, this one doesn't have 2 or 13 or 26. This one doesn't have 3 or 11 or 13. The only thing that's in common is 1 and 1. Okay, so even though neither of these numbers itself is prime, they are called relatively prime because the only factors that they have in common are 1. That's the only one. Okay. All right, so that's what relatively prime means. So thinking about that, okay, let's define a relation on a set of positive integers where x is related to y if x and y are relatively prime. Okay. So we ask ourselves about all the properties. Is this relation reflexive, anti-reflexive, symmetric, anti-symmetric, transitive? Okay. So to be reflexive, that would mean that for every single x, okay, in the set of positive integers, is it true that x is relatively prime, okay, to x? Is it true that no matter what number I pick, the only common factor that x will have with itself is 1? Pierce is saying no. I agree with him. No. Okay. So, for instance, let's say 3 and 3. What other common factor is there besides 1? 3, yeah, okay? So in general, like x and x have the common factor of x, right? So, okay. And so this one is not reflexive. Okay. So does that mean that it's automatically anti-reflexive? No, not necessarily. It's only anti-reflexive if I can never, ever, ever find a single x that would be related to itself. Okay, so we have to stop and ask ourselves, well, is there any case where I could find that a number and itself only had 1 as a common factor? 1 and 1, yeah. So it's not anti-reflexive because 1 is relatively prime to 1. Okay, that's the only positive integer that's relatively prime to itself. All the other ones, 2, 3, 4, 5, you could go on forever there. It's not. Okay, but we have just one counterexample where 1 is relatively prime to itself. Okay, so this one is not anti-reflexive either. Okay. So up here we have 2 is not related to 2, 3 is not related to 3, 4 is not related to 4. Okay, but we have one case where 1 is related to itself. Okay, so it's not always true and it's not always false. So it's neither reflexive nor anti-reflexive. That can happen. Okay, so what about symmetric? Okay, so is it true that if x is relatively prime to y, then it would have to be true that y is relatively prime to x? Okay, would that always be true? X and y are relative, so x and y, the only common factor they have is 1. So would it automatically be true that y and x only have a common factor of 1 as well? Hopefully fairly obviously, yes. X and y are still the same numbers. They still have the same factors. It doesn't matter which order I consider them in. If x and y only have a common factor of 1, then y and x only have a common factor of 1. It doesn't really matter what order I put them in. So yes, this is always true. So it is symmetric. And then the question, is it anti-symmetric? Okay. So for anti-symmetric, we have to say, all right, if x is not equal to y and x is relatively prime to y, will we get that y is not relatively prime to x? Well, it's pretty clear. If x is relatively prime to y, if that one's true, this one's going to have to be true. Right? There's no way that we could get this one not to be true. Okay. This is a definite no. If x, every time that x is related to y, y has to be related to x. Okay. And so this is not anti-symmetric. And then finally, is it transitive? Okay, so let's say if we had x was relatively prime to y and y was relatively prime to z, would we automatically get x is relatively prime to z? Okay. And that's why, like, what's your gut feeling tell you? No, right. So here we might be just come up with a counterexample. If I can just find one case where it's not true, that's all I need to say that it's not true for all values of x, y, and z. Okay, so if we just choose, like let's choose x to be just like 2 times 3. Okay, so y, for x to be relatively prime to y, y just has to have factors that aren't 2 or 3. Okay, so let's say they were 5 and 7. Okay. So we would say, okay, 6 is relatively prime to 35. Okay, that's true. All right, so if y is 5 times 7, okay, when we choose z, we're going to try to choose something so that this won't be true. Well, we want to see if we can find a counterexample. Okay, well, if z has either 2 or 3, or both of them as factors, then it will not be relatively prime to x. So let's choose, let's do 2 times 11. Okay. So these don't have any common factors besides 1. These are relatively prime. So 35 is relatively prime to 22. But then when I go and check, is 6 relatively prime to 22? The answer is no. Okay, because they both have 2 as a factor. Okay. All I need is one counterexample, but you can see, like, we could come up with lots of counterexamples. We just have to make sure that z and x share some kind of factor, but it's not in y. Okay. So this one is not transitive. All right. I'll do a few more. All right, so we've got binary relations. We want to see if they're reflexive, anti-reflexive, symmetric, antisymmetric, or transitive. Okay. This is a relation on the set of real numbers. Okay, x is related to y if the sum of x and y is 0. Okay, so let's see about reflexive. Is it true that for every x, x plus x equals 0? Definitely not. Okay. No, certainly not. 2 plus 2 isn't 0. 7 plus 7 isn't 0. There's a whole bunch of real numbers where I add it to itself, and it's certainly not 0. So this is not reflexive. Okay. So does that mean that it's anti-reflexive? Okay. So is it true that no matter what x I take, if I add x to itself, I'll never get 0? Could I ever find an x where I added it to itself and it was 0? Yeah, what is it, Josh? 0. Okay, so this is no, because 0 plus 0 equals 0. That's the only one. There's only one counterexample, but all I need is one counterexample, right? Okay, so it's not anti-reflexive either. Okay. So one thing that's tricky, I guess, about the reflexive and anti-reflexive, if it is reflexive, then it's definitely not. Okay, anti-reflexive, it can't be both at the same time, but it doesn't have to be one or the other. It can be neither as well. Okay, and we've seen, I think, 2 examples of that now. Okay, next is it symmetric. Okay, so is it true that if x plus y equals 0, then we'll automatically get that y plus x equals 0?
No.
Definitely, because, yeah, because of the commutative property. So the commutative property of addition says that it doesn't matter what order I add 2 numbers, their sum is always the same. So if x plus y is 0, it's definitely true that y plus x is 0. So this one is symmetric. Okay. And then anti-symmetric. Okay. So if x isn't equal to y, okay, and x plus y equals 0, will it then be true that y plus x is not equal to 0? So x and y aren't the same, so could we ever have a case where x plus y is 0, but y plus x is not 0? Certainly not, because we just said that the commutative property says every time x plus y is 0, y plus x has to be 0. So this can never be true. Okay. So this one is not anti-symmetric. Okay. And then the last one we need to check is transitive. Okay. So if we had that x plus y equals 0, and we had that y plus z was also 0, would it then be true that x plus z would equal 0. So if both x plus y and y plus z are 0, okay, what could we conclude about x and y? Maybe I could even do some examples like, if x were 2, what would y have to be in order for the sum to be 0? Have to be negative 2. Okay, and so if y was negative 2, what would z have to be for the sum to be 0?
2.
Have to be 2. X and z have to be the same thing, right? X and z have to be equal. So if x and z are equal, are we always going to get that x plus z equals 0? Certainly not, no. Okay. I mean, there's one case that we could get that, when x and y are both 0, and y is 0. But that's the only time it will ever happen. Every other, and this would have to be true for all x, y, and z. Okay, certainly not true for all x and y and z. So this is not transitive. Okay. All right, let's look at the divides relationship. So x is related to y if y divides x. Okay. So, is it true that no matter what x I find, that x always divides x?
Yeah.
Yeah. So, I can always write x as an integer multiple of itself, right? 1 time itself. So, yes, it always divides it, so it's reflexive. Okay. So, if it's reflexive, is there any possible way that it's anti-reflexive? Can something be both reflexive and anti-reflexive at the same time? No. I mean, now we get this one for free. Okay, so definitely not. We already said it's reflexive, so it certainly can't be anti-reflexive. Can't be both at the same time. Could be neither, but can't be both. Okay. Then how about symmetric? Okay. So that would say, if x divides y, then y also divides x. Is it always true that if x divides y, then y divides x? Can you find a counterexample to that? Give me one number that divides another number. 2 divides 6. So 2 divides 6. So does that mean that 6 divides 2? No. No, definitely not. Okay. So this one is not symmetric. Okay. So the question is it anti-symmetric? Okay. So as long as x and y are not equal, okay, when x is related to y, so if so I guess this is if y divides x, okay, then will it be true that that x doesn't divide y?
Yep.
Okay.
As long as they don't equal each other.
Yeah, as long as they don't equal each other. Okay, and that's part of what anti-symmetric is. So if x and y aren't the same, we have that at most one of these could be true. Okay, x could divide y could divide x, or neither of them could divide each other at all. Okay, so these are the three possibilities. We could have x divides y, okay, and y doesn't divide x. We could have y divides x, and x doesn't divide y, or we could have neither of them divide each other. Y doesn't divide x, and x doesn't divide y. Okay, so depending on which one is smaller or which one is larger, but at most one of these can be true. Okay, so either they don't divide each other at all. If one of them does divide each other, okay, one of them's bigger and one of them's smaller because they're not equal, the small one can divide the big one, but the big one can't divide the small one. Okay, so at most one of those things can be true. So yes, at most one of those things will be true. So this one is anti-symmetric. Okay, so you'll never have that both x divides y and y divides x at the same time. Okay, and finally, transitive. Okay, so if x is related to y, then we have y divides x. If y is related to z, that means z divides y. Okay, so if that's true, will we get that x is related to z, which means z would divide x. Okay, so notice x is related to y. The order got flipped there a little bit. Okay, so this one gives us that x is an integer multiple of y. This one gives us that y is an integer multiple of z. And so can we establish a relationship between x and z? Let's see if z divides x. Okay. Okay, so let's take this expression for z and substitute it in here. We would have x equals a times, well, y is really b times z. Okay. So since we know this is true, is it true that z divides x? Z divides x if x can be written as an integer multiple of z. Is x written as an integer multiple of z? Certainly, because a and b are both integers. Okay, so yes, it's definitely z divides x, so this is indeed transitive. Power set. We haven't seen that for a while. Okay, so that's a good one to review. All right. Let's see. So we've got the power set of 0, 1, 2, 3. Somebody remind me, what's the power set again?
Is it, it's when there's like a whole bunch of like different sets compiled into one set.
Yes. It's every possible subset that you could make using the elements of this set. Okay. So it's got every possible set that has nothing in it, which is the empty set, right? It's got every possible set that has one element. So it has the set that contains 0, the set that contains 1, the set that contains 2, the set that contains 3. It has every pair. And then it has the whole set itself. Okay. How many subsets will there be in total? 16, 2 to the 4th. There's 4 elements in here. It's always going to be 2 to the power of however many of the cardinality of that set. So there will be 16 different sets. Okay. We're not going to write them all out, but we can imagine what they would be. So there would be like 1 element sets, 2 element subsets, 3 element subsets, and that empty set as well. Okay. But we would ask ourselves, all right, for every single one of those, could I take x, would it be related to itself? That is, would x always be a subset of x? Is every set a subset of itself? Yes. Okay. Because of this little equal line under there. Okay. Now, if we said proper subset and we took the equal away, the answer would be no. But since there's a little equal line under there and it's allowed to be equal, the answer is yes. So this is definitely reflexive. Okay. So is it anti-reflexive? No possible way. Can't be both. If it's reflexive, it's not anti-reflexive. Okay. Reflexive means it's always true that x is a subset of itself. Anti-reflexive is it's never true that x is a subset of itself. Can't both be always true and never true at the same time. Okay, how about, is it symmetric? Okay, so if x is a subset of y, then y is also a subset of x. Is that true? No, definitely not. Okay, so it's not symmetric. Okay, is it anti-symmetric? Okay. So if x is not equal to y, okay, then can we always have one of these 3 cases? Okay. where x isn't a subset of y and y isn't a subset of x. Okay. Or x is a subset of y, but y isn't a subset of x. Okay. Or y is a subset of x and x isn't a subset of y. Okay. So either, oops, this is supposed to be x and this is supposed to be not. Okay, let me rewrite this one. Y is not a subset of x. So would we always have that neither of them are subsets of relationship? Okay, we would have this subset being true and that one would have to be false, or this subset being true, which would mean that one would have to be false. Okay. So is it never the case that we can have both of these things happening at the same time, basically, is what we're asking. So certainly we might have x is not a subset of y and y is not a subset of x. Okay. That's easy to see. Okay. So if x was a subset of y, would it have to automatically be true that y couldn't be a subset of x? Okay. Okay. The only, well, so you're saying not necessarily if x was a subset of y, when could y be a subset of x?
Only when it's equal. So
yeah, only when it's equal. And up here we said that they're not equal. Yeah, so that's the caveat. Okay, so we're definitely saying that x, we're not considering the case when x and y are equal. Okay, so if x and y aren't equal, we've basically taken that case away, and we know that x is a proper subset of y, and y has extra stuff in it. Okay, so there's no possible way that y can be a subset of x as well. It's got extra stuff that x doesn't have. Okay. Again, here, if y is a subset of x instead, and go the other way, and they're not equal, we've taken that away. It has to be a proper subset. X has extra stuff. So there's no possible way that x can be a subset of y, because there's extra stuff in x that isn't in y. Okay. So one of these three things will always have to be true. Okay, so it is antisymmetric. And then the last one is transitive. So let's say that we had x was a subset of y and y was a subset of z. Would that automatically give us that x has to be a subset of z?
Yes.
Yes. Okay. Everything in x is in y. Everything y is in z. And all of that stuff that was in y that's in z was also in x, right? So x has to be a subset of z. So it is indeed transitive. Okay. So that is the properties, and they're important because there are, when we put some of these properties together, they give us special kinds of relations that come up a lot, and we know a lot of things about them. And the first one is partial orders. I think this is the wrong section. I think this is actually 4. Okay, but partial orders. I think we're skipping the third section that was on composition. Okay. So for partial orders are relations that have the properties that they're reflexive, they're antisymmetric, and they're transitive. Okay, so those three things. So if we put those three things together, there's certain kinds of relations that we have. There's lots of different relations that have those properties, and they are called partial orders. Okay. So, for example, less than or equal to is an example of a partial order for the set of integers. Okay, if it's a partial order, that means that we should be able to show that it's reflexive, it's antisymmetric, and that it's transitive. Okay, so, let's look at the less than or equal to relationship. Okay, so, is it always true, okay, that for all x, okay, that x is less than or equal to x? Is that always true? Two less than or equal to 2, 5 less than or equal to 5, whatever, no matter what, is a value x less than or equal to x? Yes, because we have the or equal in there. It's equal, so it's always true. Okay, so it's reflexive. Okay. And then is it anti-symmetric? Okay. So basically that says we either have x is less than or equal to y, or y is less than or equal to x, but never both. Right, that's what antisymmetric is. We can't have them both at the same time. Okay. And I'll say when x is not equal to y. Okay. So could you ever have x and y not being equal, and then it being true that x is both less than y and greater than y? It's impossible, right? You can't have both of those things. Okay. So, oops, this is supposed to be y and x. Okay. So you could never have both of these things, x being less than or equal to y, and at the same time, y being less than or equal to x. The only time both of those could be true are when x and y are equal. Okay, but we're taking away the case when they're equal. So there's never a time when both of those things can be true at the same time. So this one is anti-reflexive. Sorry, anti-symmetric. And then finally, we need to check and see if it's transitive. Okay, so if we had that x was less than or equal to y, and y was less than or equal to z, would it then be true that x would have to be less than or equal to z? Okay, I think we already talked about this one early. Definitely yes. There's a ordering with values, and if x is less than or equal to y and y is less than z, x has to come before z as well. Okay, so it's transitive. Okay. So less than or equal is the most common partial order. It's like the classic partial order. Okay, and so the symbol used for partial order looks very similar to less than or equal, so that you get the idea when you see this. Okay, it's kind of curvy, but it expresses the idea, oh, this relationship acts like less than or equal. Okay, it's reflexive, antisymmetric, transitive. You can find an order between the elements, okay, that kind of thing. Okay, and so we might say something like this, that x is related to y if x divides z. We've already done this one before. We've shown that it's reflexive, it's antisymmetric, and it's transitive. Okay. So rather than using like a general R there for is related to z, we use this special symbol that looks kind of like less than or equal to just, when we look at this, I can visually say, oh, that's a partial order. Okay. So it's just saying that it's related. It's not saying it's less than. It's just saying there's a partial order, okay, that's created for the set of positive integers and the divides relationship. So that little symbol helps me know that the relation is a partial order. So it tells me the relation is a partial order. Okay. And the reason we call it a partial order is that we have this idea of sometimes things can be compared and sometimes things can't be compared with partial orders. So when we have a relation that's reflexive, antisymmetric, and transitive, okay, we get this, sometimes we can compare things, sometimes we can't compare them. Okay, so that's why we call it a partial order. So let's look at the definitions here. All right. So we have a domain and a partial order. So A is our domain, and then whatever our partial order. Okay. And when you pair those together, that is called a partially ordered set, or abbreviated as POSET. Okay. Partially ordered set, right? The P from partial, the O from ordered, and then set. Okay. So if we took the set of natural numbers and the less than or equal to, that's a partially ordered set. Okay. We showed that back here. Okay. If we took the positive integers and the divides relationship, that's a partially ordered set. We've shown that on a previous slide that it is reflexive, antisymmetric, and transitive. Okay. But these partial orders are actually a little bit different. Okay. So, and this one we can always compare elements, and this one we can't always compare elements. So not all partial orders are the same. So we have this idea of comparable and incomparable elements. So two elements in the partial ordered set are called comparable if either x is related to y or y is related to x. One of those are true. We can compare them in some way. They're related in some way. As long as they're related, either this way or this way, okay, then they're comparable. But it may be that neither of these is true. So if neither of these is true, then we call those incomparable. Okay, so they're not related at all. Okay. So let's look at this set of positive integers and the divides relationship. Okay. So let's think of examples of elements that are comparable, where I can either say that this one divides this one or this one divides this one. Like earlier we had 2 and 6, so 2 divides 6. Okay. So 2 divides 6, that one is true, but 6 doesn't divide true. It's anti-symmetric. We know we can't have both of them. Okay. So, but that is an example. So 2 is related to 6. Okay. Now how about incomparable elements? Can you think of two elements where it's not true that x divides y or y divides x? They're just not really, like neither of them divide each other. There's lots of examples. Just throw one out there. 2 and 9. Okay. So 2 doesn't divide 9. 9 doesn't divide 2. Okay. They're not comparable. Neither of them divide each other. They're not related, so we don't have any kind of relation. So 2 and 9 are incomparable. Okay. And so that's why we call these partially ordered sets, because in general, we have some things that we can compare, okay, and we have some kind of order between them. We have other things that we can't compare. There's no order between them. We can't say that one is less than or greater than. There's just no order. Okay, so it's partially ordered, but it's not completely ordered. Some elements are ordered and they have a well-defined order. Other elements don't have any kind of well-defined order. Okay. So if we have a set where every possible set of elements do have an order, then we call that a total order. Okay, so this is a subset of partial orders. Yes. Oh, thank you. I've started to drift, sorry. Okay, so if a total order is a partial order, so it's still reflexive, antisymmetric, and transitive, okay, but it's got this other special property where no matter what two elements I pick, I can always compare them. Either x is less than y or y is less than x. Okay. So if I do have this kind of total order, okay, I can go to my total order and I can find some kind of a minimal element. And a minimal element is if there is never a y that's not equal to x such that y is less than x. Okay, so then I would say, all right, x is minimal because I can never find a y that would come before x. So x must be like the smallest thing that there is. Okay, and if you think of this like less than or equal to, if I was thinking about like the positive integers, for example, okay, I would have like 1, but there's nothing less than 1 in the positive integers. That would be like a minimal element. I could never find any positive integer that would come before it. So that's a good example of a minimal element. Okay. And you could have a maximal element, okay, so x would be maximum if you could never find a y that comes after x. So there's not a y that's bigger than x. Okay. Now this might not be a less than relationship. It might be some other kind of relationship, but think of it that way. Okay. So let's think about the divides relationship, okay, on this set. So let's say my domain is 2, 4, 8, 16, 32. Okay, and then the way that I'm defining my partial order is that x is related to y, okay, if x divides y. Okay. So it's going to be a total order if every two elements are related in some way. And so first let's, we'll look at a arrow diagram for this one, or a digraph for it. Okay, and then look and see how we could find minimal and maximal elements. Okay, so let's start with flex 2. Okay, so 2. Okay, does 2 divide itself? Sure, of course it does. Okay, does 2 divide 4? Yeah. So 2 divides 4, we could put that in there. Does 2 divide 8? Yep, 2 divides 8, I'll put that in there. Does 2 divide 16? Of course, it divides every even number. 2 divides 32. Okay, so 2 is related to everything, okay, in some way. How about 4? Well, we already know 4 is related to 2, okay. Is 4 related to 8?
Yes.
Yeah, 4 divides 8, okay, and 4 divides itself. I forgot to put that in there. 4 divides 16. 4 divides 32. Okay, so 4 is related to everything. What about 8? We know it's already related to 2 and 4. 8's related to itself because it divides itself. It divides 16. It divides 32. Okay. 16 divides itself. It divides 32. And 32 divides itself. Okay, so no matter what two pairs I picked in there, there was some kind of relationship. Okay, so it is a total order. Okay, every x and y has either x, well, I'll go with x divides y or y divides x. Okay, that's the relationship. And then if we were looking for minimal elements, okay, so the arrows give us kind of a direction of, x will be going with an arrow towards y. So if I see that here an arrow from 2 to 4, that gives me the 2 is less than or equal to this little symbol, okay, 4. All right, so I can see that I've got all these arrows going out from 2. Okay, so 2 is less than 4 because it divides 4. 2 is less than 8, it divides it. So 2 divides all these things, but is there anything that comes in and divides 2 besides itself? Okay, so notice, okay, we're not considering the case where it's itself. So the only arrow coming into 2 is a self loop. All the other arrows are going out. So in terms of if I'm looking at this digraph, I can easily see that 2 is a minimal element because all the arrows besides the self loop are going out. So all the arrows are out, okay, besides the self loop. And we don't need to consider the self loop because that's where x and y are equal. Now, if I look at 4, I've got an arrow coming in, I've got arrows going out. There's stuff before 4, there's stuff after 4. That's not minimal, it's not maximal. Okay, 8, it's got stuff coming in, it's got stuff coming out. It's not minimum, it's not maximal. 16, stuff coming in, stuff coming out. 32, though, is a little bit different. It's got all this stuff coming in. The only thing coming out is the self loop, right? But over here, all the arrows are in, except besides the self loop. Okay. So it's pretty easy to see that one's a maximal one. There's nothing that comes after 32. Okay, that's the end of the line. Okay, so here we have that 2 is minimal. And we have that 32 is a maximal element. Okay. And every total order will have minimal or maximal elements, okay? Because every two items are ordered, and they kind of have to line up in a straight line. So what we would get, you can kind of see, yeah, the way I lined them up, you would get Well, 2 is less than or equal to, is related to 4, is related to 8, is related to 16, is related to 32, and that's the order. 2 divides 4, 4 divides 8, 8 divides 16, 16 divides 32. Because of transitivity, like, since 2 divides 8 and 8 divides 16, 2 divides 16, you're going to get that transitivity in there, but I could put them in this relationship and put them in a straight line, and I would have a minimum and a maximum. That's what makes this relationship a total order, because I can line them up from like smallest to largest. Okay, whatever small and large means in terms and with respect to our definition of that relationship. Okay. So going to the partial ordered set, we've got the power set of the 0, 1, 2. I'll just go ahead and list those out. We would have the empty set. We would have elements that contained sets that contain one element. So those. We would have subsets that contain 2 elements. Sorry. I need a little tape mark here that shows me where to. Do not move your paper past this area. Okay, 0, 1, 0, 2, 1, 2. That should be all the 2 element subsets, and then, oops, all the 3. There should be 8 total, but that's 2 to the third. 1, 2, 3, 4, 5, 6, 7, 8. Got them all. Okay. So those were our elements, and we were using the subset relation. Okay. Somewhere back on a previous slide, we looked at the power set and we looked at subset, and we showed that it was reflexive, antisymmetric, and transitive. So it indeed is a partial order. Okay. But let's look and see about the minimal or maximal elements here. Okay. So let's start with this one. Okay. If I were to take and draw this in a diagram, I might put the empty set there. Okay. Well, the empty set is related to everything. But so it's related to, it's got, it's a subset of itself. Okay. It's a subset of 0. It's a subset of the set containing 1. It's a subset of the set containing 2. But if I look at these ones right here, the set containing 0 isn't a subset of 1. And that isn't a subset of 0. 1 isn't a subset of 2. 2 isn't a subset of 1. 0 isn't a subset of 2. 2, like none of these are related to each other. Okay, so like if I look at this kind of little group right here, these are incomparable elements. So this is definitely not a total order. This is a partial order. Okay, because there's no relationship between those. None of them are subsets of each other. Okay. Then I've got these 2 element subsets, okay, and none of them are subsets of each other either. So I'm going to put my 0, 1 here. I'm going to put my, I'm going to put 0, 2 down here. No, I'll put 0, 2 here. And I'll put 1, 2 here. Okay. So 0 is an element of, it's a subset of that one, and 0 is a subset of the 0, 2. Okay. 1 is a subset of this one and this one. 2 is a subset of this one and this one. Okay. But these 2 are incomparable. Okay, the 0 and the 1, 2, those are incomparable. There's no arrow between them. This whole group right here, all of these are incomparable. That's just why it's kind of nice to put them here. Okay. And then we've got this last, oh, and then, of course, this is a subset of everything, so we should have all of these in here. And then we've got our last set that has 3 elements in it, 0, 1, 2. Okay. And everything's a subset of that, so these all are, okay. These all are, of course, this is. So there's a lot going on in that diagram, which is why we're going to find a new diagram on the next page. But here is this crazy digraph. Okay, is there a minimal element? So if we look at this digraph and try to look for a minimal element, do we have an element where all the arrows are going out except for, there should be self loops on all of these, because it's reflexive. So every single one of these things is a subset of itself. Okay, do we have anything that has all arrows going out except for a self loop?
Yes.
Yes, what is it?
Nothing.
It's the empty set. So the empty set is a minimal element. And do we have a maximal element where all the arrows are coming in except for perhaps a self loop?
0, 1, 2.
Yeah, the 0, 1, 2. Okay. Okay. So it doesn't have to be a total order to have a minimal or maximal element. You can still have a minimal and maximal element. But notice it's not like we can't, like this previous one where we could just line them all up and say this one is always less than this one is less than. We can't just line them up in a straight line like we could with the total order. Okay? Because there is no relationship between this set and this set. Okay? There is no relationship between this set and this set. So I couldn't put them in a straight line and give you a total order. I could just give you a partial order. I have like, this path, and I have this path, and I have this path. I have some paths through there where I can partially order the sets, but I can't put them all in a line and order them all. Okay. But that doesn't mean there's not, I still have a minimal, I still have a maximal, but the stuff in the middle, I don't really have any way of arranging that nicely and telling you this one comes first and this one comes second. Okay. Now, we saw there were so many arrows coming out on this one. They start crossing each other, and it's almost impossible to follow them. And you feel like there's a lot of redundance in there. Okay, so couldn't we find a better diagram to represent all of this information, but wouldn't be so messy? Okay, and that's what this Hasse diagram is, named after some guy whose last name is Hasse. Okay, so a Hasse diagram is a graph that's used to depict a partial order. It has to be a partial order. So whenever we see one of these, we know it's a partial order, either a total order, which is a special kind of partial order, but definitely a partial order. Okay. And because we know it's a partial order, we know it's reflexive. We know it's antisymmetric. We know it's transitive. And so we assume a lot of those relationships rather than drawing them in the diagram. Okay. So we try to have a minimal diagram so there's not so many extra lines in there. Okay. And so when we draw this, we show precedence relationships by placing elements that are greater towards the top, okay, and elements that are smaller towards the bottom. So where the bottom is where the small things are, and the top is where the big things are. Okay. And then it only includes enough edges to make the relationships clear. Okay. So all of the reflexive and transitive properties will be clear and we don't have to add extra stuff in there. Okay, we'll do an example and you'll see what I mean. Okay, so rules for drawing the Hasse diagram. Okay, so if x is related to y, okay, x will be lower in the diagram than y. Okay, so all of the smaller things, whatever small, however we decide what small means, will be towards the bottom. Okay, so it will be lower in the diagram. Okay, and if x is related to y and there's no z, such that x is related to z and z is related to y, then we have to draw the edge between x and y. Okay, but if we do have, a z that it's related to, we're not going to draw the edge. Okay, that's sort of don't draw transitive relationships in there. Imply those. Okay. So I will show us an example. Let's do this one. Okay. So we know from this mess of a diagram that we made that there is, an element that's lower than all the other ones. Okay, a minimal element. That's this empty set right here. So if I were to draw a diagram, I would know, well, that has to appear lower in the diagram than anything else. So my empty set would be down here. And then I'm only going to put an edge from this set to another element if I can't imply it by any other edge there. Okay. So if I think about the set containing 0, okay, I'm going to put an edge there, and it's going to appear higher in the diagram, okay, because I can't imply that relationship through any other set. I'm going to have the set 1, okay, it's going to be higher in the diagram than 0. And I'm going to have 2, it has to be higher in the diagram than 0. Okay, because this one is a subset. When I go from low to high along an edge, that implies that the empty set is a subset of the set containing 0. Okay, this is a subset, this is a subset, that relationship. Now, I consider, like, let's say the set containing 0 and 1. Okay, well, this one is a subset of the set 0, 1, so that other one's going to have to be higher in the diagram. So 0, 1 could be up here. Okay. Well, I have to put that edge in. Okay. But because I have a path that goes up like this, I don't have to put this edge in. That's implied. Because it's transitive, I know that the empty set is a subset of 0, and 0 is a subset of 0, 1. Therefore, the empty set has to be a subset of 0, 1. There's no reason for me to put an edge in there. I'm not going to put any of those transitive edges in to simplify the diagram. So that's what this rule right here says. I'm not going to draw the edge, okay, unless I can't imply it from any other edges that are in there. Okay. Let's think about the set containing 0 and 2. Okay, so 0 and 2... okay, has to be higher than 0 in the diagram. It has to be higher than 2 in the diagram. So I'm going to put it up there. Okay. I'm going to put all of those in. So this one is a subset. And then I have 1, 2. Has to be higher than 2, has to be higher than 1, because those are subsets. Now, definitely the empty set is a subset of all of these, but I'm not putting any of those edges in because I can get that simply by going along a path. Okay, so I can go along a path of edges and get there. So I know that 0 is lower and there's a path to 1, 2. So 0, or the empty set is related to the set containing 1 and 2, but I'm not putting an edge in there. Okay. And then finally, I've got the 0, 1, 2. Okay, now all of these are subsets of that, so this has to appear higher in the diagram. Okay. Okay. And the question is, well, should I put an edge between like this set and this set? Well, no, because there's a different one that it already goes to, and that's also a subset of this one. So I go to the last possible one, okay, and I put that edge in. So I'm only going to put the edge in if I can't imply it from some other edge. Okay. So this diagram and this diagram are telling me the same things, but this one has just a fraction of the edges. No self-loops. I know that it's a partially ordered set. I know it's reflexive. I know every single one of these things has to be related to itself because it's a partially ordered set. Okay. I don't put those in there. Okay. Then when I look, okay, well, how can I tell if things are like, I want to know, is this and this related? Okay. Well, the only way it's going to be related is if I can find an upward path from here to here. Can I? Well, this goes up. If I were going to want to get to this, I would have to go down and then up, or I could go up, up, and then down. Can't ever go down. Okay. If you ever have to find a path that goes down, they're not related. Okay, so these two are not related. There's no up-only path between the set containing 0 and the set containing 1 and 2. So these are incomparable, not related. There's no up-only path between them. Okay, but what about, 1 and, well, this one up here? There's an up-only path to it. What about 2 and 0, 1, 2? There's an up-only path between it, so they're related. What about this and this? There's an up-only path. So if I find any up-only path between two elements, they are related. If there isn't one of those, they're not related. Okay. Going to this one, we also drew a crazy diagram with a billion little edges in that for that one. Okay, we know that 2 is a minimal element. It would have to appear lower than anything else, so I would have 2. Okay. Well, it divides 4, so I'd put an edge in there. Okay, 8 has to appear higher than 4 because 4 divides 8. I'd put that edge in, and then there's no need for me to put an edge from 2 to 4 because there's an upward path, and I can see that 2 divides 4. Okay. 16 has to appear higher than 8 because 8 divides 16. So I put that in there, and there's no need to put any of these edges in because I have an every upward path. 2 divides 16, 4 divides 16, 8 divides 16. 32 has to appear higher than 16 because 16 divides 32. Okay, once again, I have all the paths that are in it. I see that 2 divides 32, 4 divides 32, 8 divides 32, 16 divides 32. Okay.
Is there some sort of measurement or something that people use to like define a degree of how far away something is from a total order? Because I'm looking at it kind of in my head, and I'm noticing that the more further away a partial order would be from like a total order, the more like lay out, kind of like.
I don't know. You would think that there would be some kind of, yeah.
Like based on the amount of disconnects.
Yeah. The number of like things that are incomparable. So you would have these paths. Yeah.
Total order is straight.
Yeah. So every time you have a total order, it's going to look like that. Yeah. So that's the nice thing. You can really easily see if something's a total order or not a total order because a total order, you're going to get one straight path with the smallest and the largest. And if it's not a total order, then you're going to have some incomparable things. There's no way to put them all in a straight line. Yeah, I don't know if there's any, like, I've never seen one, but that doesn't, yeah, the degree of partiality or something. Yeah, I don't know. Okay. All right, we'll end with this one. Okay, so here are some examples of Hasse diagrams. And we want to look and see if we can easily find minimal and maximal elements in each of the partially ordered sets. Okay. Okay, so there's no arrows in here. Okay, it's all about level. So low things are small and things that are high are big. Okay, so if I go to partial ordered set A, are there any minimal elements? Elements where there's nothing below them? Yeah, D. So D. Okay. And everything else, B, C, A, has something below it, so none of those are minimal. What about maximal? Are there any maximal elements? A. A is maximal. Okay. If we go to partial order set B, okay, are there minimal elements in there? F is, okay, there's nothing below F. Anything else? Yes, and E. So E over here has nothing below it. Okay, so both E and F are minimal. What about maximal? Anything maximal? Well, there's nothing above it. A and B, so nothing above A, nothing above B. Okay. Okay, how about minimal in C? H definitely is minimal. Anything else? D. D has nothing below it. Anything else? C. C has nothing below it. Okay, so all of those are minimal. So notice, okay, this one is a little bit tricky because this one could have been drawn down here, and this one could have been drawn down here, all on the same level. Okay, but they didn't. But this still has nothing below it, and this still has nothing below it. So those are still minimal. What about maximal? A and F. Okay, and everything else has something above it. Okay, and then how about this last one? Minimal. D and E. Maximal. A and B. Okay. Nothing below E or D, nothing above A or B. Okay. So the Hasse diagrams are pretty easy to look at, find minimal and maximal, see the relationships, and see the orderings. Are any of these total orders? No. It's really tempting because you see these straight lines here to think that this one is, but there is no relationship. Like A and D aren't comparable. B and C aren't, like, there's no relationship between, like, this little group over here. Like, if I have just that one, that would be a total order. If I have just that, that'd be a total order. But you put them together, it's not a total order because I have no way of knowing any relationship between A and D, A and B, E and D, E and B. Okay, so no, none of these are total orders. You would have to have every single one of them in a straight line to be a total order. Okay. All right, so we're we're almost done with the partially ordered sets. We just need to practice drawing a few more Hasse diagrams. That shouldn't prevent you from finishing the partial order set. So everything up through these partial orders is going to be due before class. I'll go on ZyBooks and put that in there. And I will see you next time, and we will finish up our few Hasse diagrams and our equivalence relations next time.